Hey everyone and welcome. So, you've probably used an AI chatbot, right? Maybe to help you write an email, fix a bug in your code, or just to ask it a silly question. But have you ever really stopped and wondered what is going on under the hood? Well, today we are pulling back that curtain. We're going to demystify the incredible tech behind tools like ChatGPT. We'll explore how they learn, how they seem to think, and what it all means.
I mean, seriously, how can a machine do all this? How can it look at a totally absurd picture like this one, with an old-school VGA cable plugged into a smartphone, and not just get the joke, but explain why it's funny, panel by panel? It feels like magic, right? But it's not. It's the result of something called a large language model.
So to really get to the bottom of this, we have to start with the basics. What even is a language model? And more importantly, what's so large about a large language model? Let's dig in.
Okay, so at its heart, a large language model, or LLM, is an AI that's built to understand and generate text that feels, well, human. The absolute key to making this all work is a piece of tech called the transformer architecture. Before transformers, models read sentences word by word, almost like they were looking through a tiny tube. A transformer, on the other hand, gets to see the entire sentence all at once. It understands how every single word relates to every other word, and that is what gives it a real sense of context. It's a game changer.
Now, these things didn't just pop up out of nowhere. Nope, they're the result of decades of work. We started way back with statistical models that basically just guessed the next word based on how often it appeared. Then we got neural models that could actually learn relationships between words. The real leap forward happened in the late 2010s with pre-trained models like BERT and the early GPTs. That's when we started training them on huge piles of text first before fine-tuning them. And that right there set the stage for today's LLMs, where just making them bigger unlocked totally new abilities.
So let's talk about that secret sauce, because this is the single biggest reason for the absolutely insane jump in AI performance we've all been seeing. It's all about scale.
See, here's the thing you have to understand. While that transformer architecture was brilliant, the revolution we're living through right now hasn't come from some brand new genius algorithm. It's come from making these existing models astronomically bigger and feeding them an almost unimaginable amount of data.
So how do we even measure how big these things are? Well, we use something called parameters. You can think of a parameter like a tiny little knob in the AI's brain that gets tweaked and tuned during training. Just look at this. Meta's LLaMA 2 model from 2023 had 70 billion of these parameters. 1 year later, LLaMA 3.1 exploded to over 500 billion. That is a mind-boggling leap in complexity in such a short amount of time.
And to tune all those billions of knobs, you need data. A lot of data. The LLaMA 3 models were trained on 15 trillion tokens. A token is basically a word, or sometimes just a piece of a word. 15 trillion. It's a number so big our brains can't really process it. It's like trying to read every book, every website, every piece of code ever written by humanity over and over and over again.
And here's where it gets really, really weird, in the best way possible. When you scale these models up to this size, something incredible happens. They don't just get better at predicting the next word. No, they start developing completely new skills that nobody ever programmed into them. This is what we call emergent abilities. All of a sudden, a model that was just built to predict text can translate languages it was never taught, or write working computer code, or solve complex logic puzzles. These skills just emerge from the sheer scale. So, what's actually in that 15 trillion token diet? Well, about half of it is what you'd expect. General knowledge from the internet, books, that kind of thing. But look closer at the other ingredients. A huge chunk, a quarter of it, is dedicated to math and reasoning. And another big slice is just computer code. This diverse mix is absolutely critical. In fact, a lot of researchers think that training on the pure, structured logic of computer code is one of the key reasons these models are starting to show off these amazing new reasoning skills.
Okay, so if these models can just develop reasoning skills on their own, that leads us to the most fascinating part of all this. How are they learning to think? Or maybe more accurately, how are they learning to simulate a thought process so well that it's almost impossible for us to tell the difference?
Yeah, this is the question on everyone's mind, isn't it? When an LLM solves a tricky word problem, is it just recognizing a pattern it's seen a million times before, or is it actually understanding the logic and reasoning its way through the steps?
Well, it turns out that a huge part of unlocking this ability comes down to how we ask the question. Look on the left, with a standard prompt, we just ask for the answer, and it gives it. But on the right, we use a technique called chain of thought, where we basically tell the model to show its work. And that tiny change makes all the difference in the world.
So what exactly is this chain of thought prompting? Well, it's pretty much what it sounds like. It's a method where we guide the model to solve a problem, not by just spitting out an answer, but by generating all the intermediate steps along the way. We're essentially teaching it to think out loud, step by step, just like a person would.
And the process is actually really elegant. First, the model breaks the big, complex problem down into smaller, bite-sized pieces. Then, it solves each of those little pieces one by one. And finally, it puts all those intermediate answers together to get to the final conclusion. By forcing it to follow this structure, it's way less likely to get tripped up and make a simple mistake.
Now, what if you could make that thought process even more bulletproof than just plain English? That's the idea behind the next evolution, something called program of thoughts. Here, instead of writing out its logic in words, the model actually writes a little piece of computer code to solve the problem. It then runs that code to get the answer. This outsources the logic to a perfectly rigorous system, a computer program, which makes its reasoning even more reliable. It's pretty cool.
Okay, so this tech is fascinating, but what does it all mean for us in the real world? Let's zoom back out for a minute and look at the actual impact these models are already having today.
The applications are already spreading out everywhere. In healthcare, they're helping doctors with diagnoses and seriously speeding up the hunt for new drugs. In finance, they're analyzing news and social media to predict market trends. They're being used to build personal tutors for students, to help lawyers sort through mountains of legal documents, and even to help scientists summarize research and come up with new ideas to test.
But, and this is a big but, it's not all perfect. For all their amazing power, these models are still really new, and there are some huge challenges we have to solve before we can truly trust them with everything.
It is so important that we're clear-eyed about the limitations we're still dealing with. Hallucination is a huge one. That's when the model just confidently makes stuff up that sounds completely plausible, but is totally wrong. Since they don't have real-world understanding, their reasoning can still fail in complex situations. And of course, there's the massive ongoing work of tackling biases hidden in the data and making sure this incredibly powerful technology is used safely and responsibly.
Which leaves us with the big, unanswered question. Are these large language models just incredibly sophisticated parrots? Statistical systems that are just brilliant at faking human language and logic without any real understanding? Or are we standing right at the beginning, watching the very first sparks of genuine machine reasoning flicker into existence? Honestly, the answer isn't clear yet, and it might just be the most important technological question of our lifetime.